right, students, welcome into week 9. We are more than halfway done with our semester. After Thursday's class, we will only have 7 weeks left. I say that because I want you to make sure you're focusing in on the CK12 work. And the reason I say that is because one of the things that is always of concern to me. So week 3 work, most people have it done. That's great. There's still this lingering little amount. But then as we progress through, those numbers go lower and lower and lower. So like I said, these units are going to remain open. And if you've been working at least somewhat, like you will not be dropped from the class, absolutely. But if you haven't even started these, then it's one of those like neglect, like you're not in the class paying attention, following along, doing the work. So that's when you should be worried. But if you've been working on them whatsoever, you'll be fine. But just don't save them all till the end, because this is pretty much all of your grade. This is 90% of your grade is the CK12 work. 10% also coming from the discussion boards. So that's that. We will get to CK12 in just a moment. So if we go to our dashboard here, what you're going to see when you log in is down here. It'll say, follow this link to the week 9 module, and it'll be down here. And once you are able to click on that link, what you will come across is this, the week 9 module. So we have our discussion board, which is the motion of objects. We have our link to CK12 in case you need it. And then here is the PowerPoint without my lecture, so without this going on. And then there will be one more subsequent page down here that will be the week 9 PowerPoint, similar to like it is up here with week 8. That will have the lecture attached to it. So those will be open and available to you. And let's see. So if we click on the discussion board, once again, do not neglect these. It's the easiest 10% of your grade you can possibly get. There's no right, there's no wrong. It's just a matter of you participating in the discussions. So like I said, it's 10% of your grade, so it can affect you a whole letter grade. It can take you from an A to a B, or from a B to a C, from a C to a D, and also reverse. If your CK12 work and the quizzes aren't the best, and say you have a C in the class on the CK12 stuff, well, these discussion boards can bring you from a C to a B. Or if you're at a B, you can go from a B to an A. So do not neglect these. I really appreciate everybody who's participating. I do read every single one of them. And I really like just the honest replies that I'm getting. Some people get kind of frustrated by these, and they express it in the discussion, which is fine. Some of these topics are very abstract and out there, meaning that it requires a really strange level of thinking. But it's kind of good for us to be uncomfortable in our thinking at some points. That way we can grow in both our mindset and our abilities and our resolve. So now that I've given you that pep talk, you see here, there's this little video which says, how fast are you moving right now? So this week's work deals with objects in motion, and it sets us up for next week, which is Newton's laws of motion. So it is really important that you pay attention to this week and you sort of get the concepts down, because when we go into Newton's laws of motion, it'll be referencing a lot of the stuff that we learned this week. So this talks about how fast you're moving right now, but it brings up a really important point, which I have bolded and italicized here, that speed and motion are measured relative to something else. Believe it or not, as you're sitting there watching this, the Earth is rotating. The solar system is rotating. I'm sorry, it took me a while there. The galaxy itself is rotating. And so we have all these different types of motion, but it has to be relative to something else. And we'll get into that into the lesson. But this really talks about that, and one of the questions is based off of that. So you will see this discussion. It should be your starting point. This will give you a good primer on the unit coming up. And then once you are done with that, you will go, so here's the CK12 link, just as before. It'll take you right to the page. And once you go right to the CK12 page, in the assignments, boom, there we go, week 9, objects in motion. And so you'll notice, once again, if you click on this one, so there's only 4 sections here. And so I tried to minimize it because This one can get to be a little bit of a headache. There is math involved, but your quiz questions will not have the math involved. The adaptive practice might. So it's really important that you go in. And so if you go into motion, it's really important that you click on these and read them. Because this gives you a great background, gives you good information, and tells you how to solve the adaptive practice problems that follow each section. And so, of course, like when you go to speed as well, you're going to have real world examples. Those are invaluable. You'll really want to use those to sort of solidify these ideas in your head, because emotion is something that affects all of us, and it's an important thing. And then lastly, we have our week 9 quiz. So it's just about 4 or 5 questions from each of these sections. And I tried my best to leave all of the mathematics out, meaning that you don't have to solve anything in there. I want to focus on the concept more than I do the arithmetic. If we were in class, sure, we would take time and we would do all the math out, but I really want to focus on the concepts of this class. So you can see here, I have assigned it starting today, which is actually Wednesday. Then I had to put a due date on. They stay open. You can work on these up until the very last day of the semester, but don't save it for the very last day of the semester. You don't want that to happen. So that's your work for the week. And remember, let me just click on velocity here. The adaptive practice part, this is required. So the adaptive practice part is required, and you need these other resources to really do this effectively. So please make sure you're doing the adaptive practice. That is like our classwork. So it's almost like if I were there handing you out a worksheet. So I can't give you the worksheet in this distance learning format, but the adaptive practice works as our worksheets in our classwork. And then the quiz, if we were in class and this was a normal semester, you would have a nightly quiz. Therefore, I always put a quiz attached to our classwork. So that's that. Now, next you'll have the week 9 PowerPoint without a lecture. So we just have this link here that takes you right to the Motion PowerPoint. See, there you go. And it'll be ready to go for you. And so you can have this up while you're doing the CK12 work, so you can flip back and forth. It'll probably make it a lot easier. And then you will, like I said, let me go back real quick. You will also have another link down here that will say week 9 PowerPoint with the lecture. That is me talking. So, all right. Might as well not beat around the bush, and let's hop into our PowerPoint for the evening. So, like I said, we were talking about motion. Typically, this would be chapter 12 if we have the actual textbook and we're working out of it. So you just have to take my word for it. That's chapter 12. So first thing we're going to talk about, and they talk about this in your unit, is your frame of reference. Or when the question is asked, like, why is motion measured relative to something else? This is the same thing. Your frame of reference is your relative speed or relative motion. So by the end of this little section, we want to be able to say that we can do this, that we can explain why all motion is relative. So first off, let's talk about that term, something being relative to something else. Now, let's say, so perfect example, at the school I teach at, there is a teacher who is very short. She is about 4'10", so very short. I'm 6'3". So relative to me, she is very short. Now, to an infant or a toddler, she is not short. She is tall. Just how, relative to Shaquille O'Neal or Anthony Davis of the Lakers, I am short. So it's all how you measure it against something else. So being 36, I could say that I am old compared to an elementary school kid. Or I can say that I am young relative to like a senior citizen. It's all what you compare it against, and motion and speed are no different. So when we are describing something that is moving, you are comparing it with something that is stationary. That's what you're comparing it against. So if you've ever been pulled over and like the officer used like a radar gun to determine your speed, he was standing there still shooting that radar gun. And and we learned a little bit about a week ago about radio waves bouncing off, and that's how they would measure the speed. He is measuring your speed relative to him being at 0 miles per hour. So he is stationary, he is not moving, and that's how they are able to, he or she, and that's how they're able to determine your speed and see if you were speeding. All right. So your frame of reference is the background of the object that is being used for comparison. So this example here, say if you got on a train and you left the platform, to anybody else who's still there on the platform, they see you moving away. So you are moving relative to the earth, to the platform, to the ground, whatever you want to call it. But if you're sitting next to someone on the train, they don't see you moving. You're not moving relative to them because they're moving with you. Anybody on the platform sees you moving relative to them because they are stationary. So you may want to watch or listen to that portion a couple more times because it's a little bit hard to get into the brain. All right. So the frame of reference depends on the type of movement and position which you are observing. So an actor may be standing still and the background is moving. So if you think of like a play where they use like a rotating background, or if you think of video games, most video games, even though it looks like you're moving through this giant like map of different areas, you are pretty much stationary and it's just the background changing around you in those video games. So it's pretty cool. But so if we take that example of an actor and say like the background is moving behind them, we're led to think that the actor is going somewhere when he's not actually moving. So we're assuming that the background is stationary. And so in most of our examples in this unit, and as they talk about in the discussion board video, Earth is the most commonly used frame of reference. So when astronauts blast off and they're going to a space mission, whether it be the space station or to the moon or to Mars, their speed in space or their motion in space is measured against the Earth. How far are they moving away from the center of the Earth? So that is the frame of reference for space travel. So any astronauts, when the astronauts were going to the moon during the Apollo missions, and they were asked, for a speed reading, well, that speed was based off of their position relative to the center of the Earth, how fast they're moving away from it. So that's just saying Earth is the most commonly used frame of reference, and we will use it many, many times. So now we can say why all motion is relative. You need a stationary object to measure motion away from or towards a certain object. All right, so now as we move into motion, we want to be able to do all these things. You want to be able to define motion and speed. You want to be able to calculate it. Now, we're not going to do a bunch of tricky calculations, but we do want to use this basic formula of speed being distance over time. And we're going to see how just using the formula units for that equation, you can kind of get an idea. So for us, distance is usually measured in miles, and then time, it could be seconds, minutes, or hours. But if we put hours down there and it's miles over hours, that is also saying miles per hour. That's how we usually measure our speed when we're driving, right? Or flying, or taking a train, or running. I don't know. Maybe you're on a unicycle. Whatever you want to do, it's fine with me. So you also want to be able to distinguish between a constant speed and an average speed, which we'll get into. And then you want to be able to see speed on a graph as a function of distance versus time, and then be able to distinguish between speed and velocity, which are two, I'm not going to say different things, but they sort of carry a different meaning with them. And so we'll get into that. So motion, just plain old motion. It's one of those things, if I were asked you to describe right away, tell me motion. I'm moving, but that's once again like the answer can't be part of the original question. So let's have a better definition of motion as we're going through this. So motion, just simply stated, is a change in position in a certain amount of time. So how far did I move away from my original position? In a certain amount of time. That's all motion is. So when you say that something is moved, you are describing the motion. So if I were to get up from this room and go to, my kitchen, that is motion. I have moved from one room that I was in to another room that I was not in. There's been motion happening. And so like we said before, in describing motion, like I just did, saying I was in a room and moving to another, I am providing a frame of reference. So we need those things. There needs to be something that has moved, and we need a frame of reference. All right, speed. So in a race, if we're thinking about a race, so the runners have to move or change positions to get to the finish line in a certain amount of time. Obviously, you want to be the fastest one if you're racing. So to describe motion, there's two things we need to know. We need to know the distance that was traveled, and the standard unit for distance is meters, we're used to hearing like feet or miles, but if we want to use the standard unit of measurement, it will be in meters. And then we also want to know how long did it take, which will be measured in seconds. It's just an easier way for us to measure it. And so that is our units for speed, meters per second. So speed overall is just the rate at which an object moves. And the faster the runner's rate of motion, if we're going back to that rate, the faster their speed. So the quicker the motion is, the faster the speed is going to be. It sounds very common sense for sure. It's something we want to make sure that we have implanted in our brains. Speed just being distance divided by time, and our units being meters per second. So we're getting the units in, we're understanding what speed and motion are, and now we're going to start to piece them together. So let's first talk about constant speed. So objects that are in motion and their speed doesn't change, we say that is a constant speed. So for that, we just take the total distance divided by the total amount of time at any point in time. And so if we look at the graph here, I'm going to use my little cursor here. So this graph is a straight line for constant speed, meaning if we start at the beginning point of the graph, which is essentially 0, 0, and we have this uniform velocity going out, we have a constant speed. Where if you were to measure the slope of the line from, time 0 to time 1, it is going to be the same slope of the line from time 1 to time 2 as to time 3, 4, 5, and 6. And so that would be our constant speed because it's not changing. Now, this is not how it usually happens, though, and we're going to get to that in a second. So if we just think of that, let's try and solve this problem. So what speed would a plane be going if it traveled 1,760 meters in just 8 seconds? So that's really, really fast. And so if we just use that formula of speed being distance divided by time, the distance that it gives me is 1,760 meters, because we said distance is always measured in meters, divided by the amount of time it takes, which was 8 seconds. If I do 1,760 divided by 8, I get 220. If I throw my units on there, it would be 220 meters per second. That is the speed at which the plane is going. So 220 meters per second, very, very fast. And that is a way that we would get to it. So if you have the adaptive practice and they're asking you to find speed, boom, this is how you do it. Done and done. So average speed. So if you think about when you're commuting somewhere, if you're driving somewhere, like if I were to go from my apartment to my classroom at Valley View High School, well, I'm not going at constant speed. I'm not getting in the car and it's starting off at 60 miles an hour and I'm going that way the whole time or that fast the whole time. It takes me a little while to get to the freeway. I'll accelerate and then I'll have to, brake because there might be a red light. And then the speed limit on those streets maybe is only 35. And then once I get to the freeway, speed limit 65, but I'm really going 85. And then there might be traffic, so I've got to slow down a little bit. So my speed wouldn't be constant. And so we want to look for an average speed. And we do it the same way. There's no big difference here. So not all objects are going to be moving at constant speeds. And the average speed also uses the same formula. The total distance divided by the total time. That gives us our average speed, as opposed to an instantaneous speed. Like, say if I'm going 85 on the freeway, that is my instantaneous speed. It is not my average speed. Once I get onto the city streets and I'm maybe having to go 40 miles an hour, 40 miles an hour is my instantaneous speed, not my average speed. So say if I was going to Las Vegas, so I would be changing speeds many, many times because there's, certain times where it's trafficy. Then once I get out in the middle of the desert and there's not many CHP around, I'll fly. I'll go 80, 85, so it's going to be constantly changing. So overall, if I wanted to find the average speed I'm traveling at, if you look at this graph here, maybe from 0 to time 6, I was going this fast, and then I leveled off. I didn't change my speed. And then from, time 14 to time 18, I increased. Maybe there was no cops around, so I put the pedal to the metal, went a little faster. If I just took the average of all of these different speeds, once again, my total distance divided by my total time gives me my average speed, how much I was going or how fast I was going over that amount of time, and how much distance I covered. All right, so now we're going to leave speed in the rear view mirror for a second. That's kind of a nice pun, right? And then we're going to talk about velocity. So velocity is a speed in a given direction. That is the biggest difference between speed and velocity. Speed is just distance divided by time, and that's it. Velocity, there's distance divided by time, and then what direction are you going? Now, your CK12 unit gets into vectors a lot, and vectors just sort of show the direction that you are traveling. We don't get too heavily into physics here, so we don't have to worry about vectors too much, but since your adaptive practice does talk about them, it is worth mentioning, and we will talk about them again at the end. So velocity is just a speed in a given direction, meaning maybe I'm going 80 miles an hour north, or if I'm going to Vegas, I'm going northeast from where I'm driving, or from where I started, rather. So it is also determined by using the distance from the starting position to the ending position, rather than the distance of the path taken. Meaning that maybe there's a detour on my way to Vegas and I have to go east for a while, then maybe I'm going to go south for a little bit, and then I get to wrap around and maybe have to go back like northwest. Well, it is only from the starting position to the ending position. So you just look at that direction from the start to the end, and that is your vector. So if I'm going northeast and it's going this way, no matter what path I took, that would be my vector, northeast, from where I started to where I finished. So we said that a runner moves eastward at 10 meters per second. It is no longer just a speed. Now we have a velocity. So the speed is the 10 meters per second. The velocity is 10 meters per second east. All right? Hopefully that makes a little bit of sense. So velocity becomes very, very important. So if I'm just driving on the freeway and I said, I'm going to work and I'm going, 70 miles an hour. Okay, all well and fine. For me, giving simple instructions or just making a simple statement, that's totally fine. But if you're like a pilot, or if you're doing like weather forecasting or anything like that, you need the direction. So you don't hear a weather person say like, the winds are at 20 miles an hour. From where? Where is it coming from? So that's where they'll always say they're 20 miles an hour coming out of the northeast, or we have an onshore flow. Even though you hear onshore, you don't think that's a direction. If you're on the west coast, that means that the wind is moving east. If you're on the east coast, that would be a wind moving west, because you have a relative position to talk about. Hopping back to the relative position. Pretty cool, right? All right. So it is really important for pilots and weather forecasters. And if you're just given basic directions, you would want to say, the direction. 60 miles an hour east, that's the way you're going to go. So that is velocity, putting a vector on it. So now let's see the things that we can do. Can we define motion and speed? Yep. Can we calculate speed? Yep, we just did it. Can we distinguish between a constant speed and an average speed? Sure can, we did. And can we represent speed graphically? Yep, we did that, we showed it. And then we also distinguish between speed and velocity, saying that speed was a distance over time, velocity is distance over time with a direction. So if we talk about changes in velocity, we want to be able to do these four things. Define acceleration and deceleration, which is also negative acceleration. You want to be able to sort of calculate acceleration and deceleration, meaning that I'm not going to ask you math questions like that on the quiz, but your adaptive practice probably will have those questions in there. And can we interpret the distance time graph for acceleration and describing circular motion a little bit, and then we're going to be finishing on up. So acceleration is the rate of change in velocity. So we said, velocity was speed with a direction to it. Well, now, like we were saying before, like velocity is just your starting point to your end point. Well, now maybe we have to go a little bit further in one direction, then go another direction, and we have these changes in velocity because we're still going a certain speed in a certain direction. But when we have to look at like the average or the aggregate of it all, now we're talking about acceleration. So if something is accelerating, it is doing one of the following things. It is either speeding up, slowing down, or changing directions. If any one of those three things is happening, you have a change in acceleration. So here's our way to calculate acceleration. Your final velocity, so speed and direction of the final part, your original speed and direction, so your original velocity, divided by time. We see here that both of these, speed, velocity, and acceleration, always have time as the denominator, like the determining factor. So acceleration just being the final velocity minus the original velocity divided by the time. So it tells us how fast something is going and tells us the direction it's going. And it is used when we have changes in velocity. When you have changes in velocity, you're going to have changes in acceleration that have to be taken into account. Very important for air travel, space travel, just because with air travel, not only is the plane moving in a certain direction, but also the Earth is spinning, and it's around Earth. Despite what you may have seen on YouTube, the Earth is a sphere; it is not flat. Therefore, it makes like traveling in a plane or air travel have to go in these big sort of parabolic arcs across the sphere, which is the Earth. So now, when there's a decrease in velocity, meaning that the speed and direction have, or the speed has gone down, and so we have a decrease in that velocity, the acceleration then becomes negative, and we call that deceleration. Your CK12 unit will often go by negative acceleration, but just know that negative acceleration is considered deceleration. So the distance and time graphs for acceleration always curve, because as we go forward in the time and the distance changes, this right here is a graphic representation of acceleration. So we can see here as time goes on, maybe we have a constant acceleration here or a semi-regular acceleration. And that's why we have this nice smooth graph, but it can often change. Okay, so they don't talk too much about acceleration. I just wanted to hit that part. Let's go to the wrap up and the cheat sheet. So if you click on that, which will be part of the PowerPoint, these are all parts of your CK12 unit. I pulled them right out of there so we can sort of see what they're talking about. So we have defining motion, which we can now do. It's just defined as a change in position, and an object's position is the location. So that's where we need that frame of reference, the relative to something else. Very important. We talked about speed, and we said that we can find that by just dividing distance over time, and we have those standard units of meters per second. Now, your CK12 unit, or the question it asks you, may be in miles per hour. Maybe it's in kilometers per hour. But either way, it's still just that distance divided by the time. And we talked about instantaneous speed as opposed to average speed. Instantaneous is how fast are you going at that particular second. In that instant, how fast are you going? To where average speed is how fast are we going over the course of this amount of time. So if you were driving for an hour, how far did you go divided by how long it took you, and that's your average speed. So speed and direction give us a velocity, and like I said, your CK12 unit will focus on vectors a little bit. So the vector just shows the direction in which the object is traveling. So you could be going 60 miles an hour, which is a speed, but if you're going 60 miles an hour to the northeast, now we have a velocity. You've added on the magnitude now. And we talked about acceleration. So acceleration is a change in velocity. So we have that final velocity minus the starting velocity or the original velocity divided by time. And acceleration is something that we can feel. So if you've ever been on a plane and you're like taking off, when they start to put on the jet engines and you feel like pushed back into your seat, you're feeling the acceleration, the velocity is changing. Now, when the plane lands and they have to slam on the brakes, once again, your velocity is changing. Your acceleration is changing. You are decelerating at a very high rate. Therefore, you can feel that acceleration. When you're in your car and let's say if you're on the freeway and you're going through a big bend and you feel almost plastered up against the side, that is circular motion in which you're feeling the acceleration push you towards the outside of it. And so that's what acceleration you can really feel. When you're in your car, if you slam on the gas, you feel pushed back a little bit, you're experiencing acceleration. Hit the brakes, negative acceleration. And so these are all the terms that you're going to see in the CK12 unit. That's all the work you have to do. If you have any questions, always email me on Canvas. Sign up for Remind. The links are on the Canvas page. You can send me a regular email, and I will respond to you as quick as I can. Please be a little patient because I am teaching during the day, and therefore I might not be able to get back to you until the afternoon or evening. Other than that, please make sure you are getting the CK12 work done. Please make sure you get in there and participate in the discussion board. I thank you all for joining in, and I will see you either tomorrow in the Zoom or I will see you next week on the lecture. Have a good one.